right, so we're going to talk today about using C++, the C++ standard library for real-time audio. Although, as we're going to see in this talk, real-time actually has to be kind of in quotes because it's not actually real-time. So we're going to talk a little bit about what that even means. So what do we actually mean by real-time? And the other thing that's kind of being thrown around a lot, especially by people who are maybe not audio people, but work in video games or high-frequency trading or stuff like that, is low latency. So what's low latency? What does it have to do with real-time? Well, so if you think of like a program, as code that's doing something on some data, and you think of it as a pipe, where water flows through, which is the data. We basically have these like two orthogonal aspects of performance, right? So we have bandwidth and latency, right? So bandwidth is kind of the thickness of the tube, how much data you can like your throughput per second or per minute or whatever. And then the latency is basically how long does it take between like you asking a question and you getting a result. And those two aspects of performance are kind of orthogonal. And in audio, typically, we don't care that much about bandwidth, at least when you compare it to something like a web server or something. We're not churning these kinds of amounts of data. But typically, we do really care a lot about latency. And actually, we want to kind of put an upper bound on what this latency is allowed to be. And that brings us to kind of the first kind of simplified definition of what real-time actually is. So if you're programming for real time, it means that in order to be considered correct, not only does your program have to produce the correct result, but it also has to do that within a certain amount of time. And if it takes longer than that, then basically the result doesn't matter anymore. Your program isn't working correctly anymore. So if you're doing audio processing, I don't need to explain to anyone in this room how this works. If you're doing audio software, you typically have something like a process callback here. And then you're going to get this regularly, in some kind of real-time thread or high-priority thread. And the interval between these callbacks in a typical Windows, Mac OS, iOS, Android, Linux environment is going to be something between 1 and 10 milliseconds, which is kind of depends on your settings of buffer size and sample rate and things like that. And then when this process callback is being called, this is kind of a bit oversimplified. Like the signature here might be a bit more complicated. But anyway, you have to write your data into that buffer, right? And that's then going to be sent out the speakers. And the user's going to hear that. And if you don't do that in time, by the time the next callback comes around, you're going to have garbage in the buffer that's going to be played back. You're going to get an audio glitch. Nobody's going to buy your product. That's very sad. And so there's a little bit of a difference here between audio on the one hand and other kind of low latency industries on the other hand. So for example, if you do high frequency trading, you really want to be the fastest. You really want to have the lowest latency possible. So it really, really matters if process takes 1 microsecond or 1.1 microseconds, because in that fraction of a microsecond, you could lose $1 million. So you really want to be faster than anyone else. In audio, you don't care that much. Normally, if something takes 11 microseconds or 10 microseconds, as long as it doesn't take more than these 11 microseconds 100% of the time, and there's not ever a case where once in a while it takes 1,000 microseconds, right? Because that's when you get your glitch. So yeah, it's a little bit of a different use case. We care about kind of, can we put an upper bound on the worst case of how long something takes? And why do I put real-time in quotes? Well, if you're making audio plugins or DAWs or this kind of audio software, then typically you are doing this on consumer hardware and a normal operating system. So Windows, Mac OS, iOS, Android, Linux, those operating systems are not real-time operating systems like the one you would find on an airplane or in a car or in an elevator, right? These are regular consumer operating systems which don't have kind of a hard real-time guarantee. They don't have a deterministic threat scheduler where you have a guarantee that your callback is definitely going to be called within that amount of time. You don't really have that. You don't control the threat scheduler of the operating system. It can just decide to do something else, right? So what we do is we just do a high priority thread, and then we just hope that the OS is going to do the right thing, which it does, right? So it actually works, right? We are building audio software. It's working, so it obviously works. But this is kind of why real-time is in quotes, because you don't really have like a deterministic threat scheduler like you have on an airplane or in a car. You are kind of at the mercy of the quality of implementation of the operating system. And kind of in this talk, I'm considering these kinds of systems. So you have the other thing, you typically want to be cross-platform if you want to ship on Mac and on Windows, right? You are a normal consumer machine. You are not typically always on a high-end machine. And you're using, if you're doing C++, which I think probably a lot of people in this room do, if you came to my talk, then you just have a normal C++ compiler, right? So you don't have some kind of like special branch of Clang which you tune and special kind of Linux kernel that you tweak for performance, which is what the finance people, for example, do. You just have a regular, like out-of-the-box compiler, Clang, GCC, Microsoft, and just use that compiler, that standard library also that ships with that, right? And the other interesting thing about audio is that only part of your program is actually subject to these real-time constraints, right? So you typically have like this audio thread that's processing, but you also have a GUI, and maybe you get some stuff from the network or from the disk or whatever in other threads, right? So you have like other things going on which are not subject to these real-time constraints. But like, yeah, so in this talk, really it's about this kind of real-time in quotes bit and what you can and cannot do there. So if you have this callback here, we might, very simple, you might fill it with some audio samples, you might apply some gain. So we're calling some functions here. And the question is, well, can you call these functions in here? Are they real-time safe, or might they cause a glitch? And there are some properties, right, that these functions need to have in order to, for you to be able to safely call them inside the process callback. And they're these here. So what you want to do is you want to make sure that the worst case execution time is deterministic, that it's known in advance, that it's independent of data that's coming in that you don't know what that's going to be, and obviously that this upper bound on how long this code will execute is actually shorter than the deadline that you have. And also the code shouldn't fail. Obviously, sometimes it will fail, but then you need to have like a backup mechanism, right? You can't just throw an exception and do nothing. You have to at least output silence, right? You do have to do something reasonable. You can't just throw up your hands and give up. Or maybe you can, but then the user has to restart the program or something like that, right? But you need to approach error handling maybe in a different way than you would do for other types of apps. And so the other thing is also this kind of known in advance is also take this with a grain of salt. You don't have to micro benchmark every function and measure how long it's going to take. You can basically infer these properties by looking at what properties these functions have. And by that, you can kind of infer that it has these properties. And some of these properties are here. I think these are kind of the most important ones. You don't want to call anything that might block, which includes acquiring a mutex, allocating or deallocating memory, do any kind of input-output. You don't want to interact with the thread scheduler or the operating system in any way, because that's not deterministic typically. And you don't really want to do any other system calls. And by extension, you don't really want to call any third-party code unless you know what's going on there and unless you know that's real-time safe too. The other thing is that you don't want to call algorithms that have non-constant complexity, where you don't know how long an algorithm is going to take to complete, or it maybe depends on the amount of data and you don't know what that is. So that also means you can't use algorithms with amortized constant complexity. Typical case is inserting into a hash map, right? Most of the time, it's constant time, it takes the same time. But once in a while, a hash map says, oh, okay, now I have a cache collision, I need to rehash everything, and that's going to take a while. You don't want to do that in a processing callback, right? And so this stuff, I have done talks on this before. Other people have done talks and written blog posts about this, how to program in this style. So I'm not going to repeat all the stuff here. This talk is really about which parts of the C++ standard library are real-time safe. Basically, if you want to do this stuff, which bits of the C++ standard library, the way it comes out of the box with your compiler, are usable to do this. Because C++ standard library is great, right? It's just there, it's for free, you can use it. You can rely that it's implemented correctly most of the time. And so obviously in this talk, we're not going to go through every single function, every single class in the standard library, because we have less than an hour. But I will mention a few particularly common or particularly interesting utilities in the standard library. And more importantly, I'll tell you how to squint at the C++ standard in such a way that you can kind of figure out on your own if something's real-time safe or not. And that's kind of really the goal of this talk. So if you look in the C++ standard, which is this 2,000-page document or you can also find it on eu.is/C++draft, or there's also CPP reference, which is not quite the standard, but it contains a lot of the same information. Turns out C++ standard says nothing about execution time. You will not find anything in the C++ standard saying this function is guaranteed to take less than this amount of time. That's just not a thing in the standard library. Also, the C++ standard doesn't say function f doesn't allocate memory. That's also not a thing that the standard ever says. What you can do, though, is you can infer from the way it's specified in the standard that allocations are not needed. And then you can rely on your standard library to just do the right thing and not allocate if it's not necessary, right? So sometimes in the standard there are useful sentences like f might invalidate iterators, and then you know, okay, maybe it's going to like reallocate, the elements of the container, and they're going to be somewhere else, so that's going to involve an allocation. Or sometimes it says, if there is enough memory, this function does this, otherwise it does that, which then again means it's going to try to allocate memory to do like a faster implementation of something, and stuff like that. Also, the C++ standard never says this uses locks or this doesn't use locks, right? It doesn't say that. What it says, though, is, class X may not be accessed from multiple threads simultaneously. And then you know, okay, well, probably there's no locks in there. Or it says X may not introduce data races. And then you say, okay, then you think, okay, probably there are locks in there. So you kind of have to infer the stuff from the way it's specified. So using the C++ standard library, like for real-time code, isn't really an exact science. So because to a large extent, we do have to trust the quality of implementation. So if the specification allows an efficient implementation, you kind of need to trust that the library implementers did the right thing and did a good job, and it's going to be that implementation, basically, and it's not going to do some random allocations that are not necessary. And also, it's the same as we trust the thread scheduler of the operating system to not do anything stupid, right? So we're kind of at the mercy of these things, but most of the time they work quite well. Okay, first feature we're going to talk about is exceptions. A lot of the standard library uses exceptions. Exceptions are not real-time safe. There's work being done to change this. There was this proposal by Herb Sutter a couple years ago. Zero overhead deterministic exceptions. Maybe some of you have heard about this. So he's trying to specify a new mechanism for exceptions in C++ that you could reason about, like that would be deterministic and wouldn't have this overhead. But we don't know if that stuff is going to ever make it in the C++ standard, right? And the key sentence about what's happening right now is right here in the standard. Today's dynamic exception times do not have statically boundable time costs. In particular, throw requires dynamic allocation, at least on some systems, right? So throwing an exception is just not real-time safe. You can't do it. A question, though, which is a bit more interesting, which Fabian, I don't know if he's in the room right now, but asked me, and I couldn't really answer, is it real-time safe to have a try block and enter and leave it if you don't actually throw an exception? You have try and catch, and you don't throw an exception, but you go through that. Is that real-time safe? And I didn't really know the answer to that. Turns out it's quite complex. I had to dig through a lot of material to figure this out and ask smarter people how this works. Turns out the exception implementation really depends on the ABI, the application binary interface. So basically on your platform. And there's basically two ways of implementing exceptions. So you need all this information in order to unwind the stack when an exception is thrown. You need some extra information to do that. So either you generate all this information up front in static tables, or you generate that information at runtime when you're entering the try block. Those are basically the two ways of doing it, oversimplifying. And it turns out different ABIs are doing different things. Most of them are doing the static table thing, which is also called the zero-cost exception model, where all the information, how to unwind the stack, is kind of generated up front. So there's no extra runtime cost. I mean, it's also kind of simplified because what do you compare it against? For example, if you have a try block, you do have these instructions in there for the catch, even if you don't go there, they're there. So they might interfere with how the rest of the code is optimized and stuff like that. So it's kind of a bit more complicated than zero cost, but to a first approximation, we can say it is basically zero cost as long as you don't throw an exception. It doesn't cost you anything at runtime. And the Tanium ABI is doing this approach, so that's GCC and Clang. Microsoft compiler 64-bit is using this approach. The ARM ABI, 32-bit, 64-bit, ARM7, ARM8 is also using this approach. So there we're good. And then there's Windows 32-bit, which I don't know if anyone's still shipping 32-bit plugins on Windows? Apparently not. Okay, great. So there, unfortunately, the default exception handling model is such that the information about how to handle exception is generated at runtime when you enter a try block. So there's going to be a bunch of instructions generated. If you enter a try block, there's like stuff being written to some like thread local info is being written in some places for this like unwind info to be generated. So even if you don't actually throw an exception, you're paying a cost for that. But it turns out that cost is actually, there's nothing going in there like a lock or like a memory allocation. So everything I could see in a Windows 32 ABI is like writing a few words into like thread local memory, basically. So I didn't see anything. Yes, it's a runtime overhead, which is measurable, but I didn't see anything in there that didn't look real-time safe. So yes, it's an overhead, but as far as I can tell, it's real-time safe. Therefore, on all platforms that I have ever worked on, yes, entering and leaving a try block, if you don't throw an exception, is real-time safe. So that's good news. If you want to know more about this, there's this paper by Ben Craig where he is benchmarking the cost of throwing exceptions or using try and catch blocks on different platforms. So there's a lot of material about that. All right, so we talked about exceptions. Let's talk about STL algorithms. Which STL algorithms are real-time safe? We have a lot of them. Like is std sort safe? Is std rotate safe? So we have to assume, if you talk about this, that the actual element type and the iterator that we're using, that's real-time safe, right? So obviously, if the element type is like std string, right, and if you try to then std string allocates when you copy it, right? Or if you have if your iterators that you're plugging into the standard algorithm are back insert iterator of vector, then yeah, that's going to be allocating because it's going to be doing pushback into a vector. Or if it's like an OStream iterator, it's going to do I/O. So let's assume like we don't do any of the stuff. We just have simple iterators and we just have ints or something as the elements. Is a standard algorithm like std sort or something going to allocate memory? And it turns out the standard doesn't say. But for almost all of them, if you look at how they're specified, the optimal implementation of the spec does not require allocations. So that means you can pretty much trust that your standard library is going to implement that. It's not going to allocate memory there. A few algorithms are not like this, because for them, if you allocate additional memory like a scratch buffer, there is a faster implementation in that case. So they will do that if they can. They will allocate this like temporary buffer in order to fall back to in order to use an implementation that's faster. But you can spot that. If you look into the C++ standard, whenever an algorithm does that, it has this thing. It says, if enough extra memory is available, it's going to do this. Otherwise, it's going to do that. And whenever you see those magic words, you know, OK, that's going to try to allocate memory. And that's the case for exactly 3 algorithms: std stable sort, std stable partition, and std in-place merge. I think the only one that I've actually seen in real life, like in an audio engine or something, is std stable sort. Don't use that, please. That's not real-time safe. Implement your own or use a different algorithm. It's going to try to allocate memory. So that's probably the one that's most likely people actually use somewhere. So those 3 are specified to not be real-time safe, essentially. And then, of course, also the parallel versions of the STL algorithms for obvious reasons, right? If you have multiple threads going on, or multiple, if you have parallelism going on, that's probably not going to be real-time safe either. OK, we talked about STL algorithms. Let's talk about STL containers. Which of the STL containers are real-time safe? So obviously, we have std array, which is just on the stack. So that's safe, except there are a few functions in there that might throw, so don't use those. All other STL containers use dynamic memory, like vector, dec, map, set, all of them. So they're not real-time safe out of the box. They're just not. OK, but what if you do have a dynamically sized, if you do need a dynamically sized container? What do you do then? So one thing that I've seen in audio code is some people use variable length arrays, which is this like C syntax where you just specify the size at runtime. And I've seen DSP engineers do that. In fact, I once worked with a DSP library, which was quite extensive, where everything was done like this. Which is very unfortunate, because that's standard C, but it's not standard C++. Like, you cannot have a variable length array in standard C++. It's not part of the language. GCC and Clang support it as an extension, but Microsoft doesn't. So if you want to try to compile this on Windows, you get an error. And so with this DSP library, I had to go in and manually replace all the VLAs with kind of custom containers. It was quite painful, so I hope you don't have to do that anymore. Okay, so don't do this because it's not portable. What else can we do if you just want to use the standard containers? Okay, standard containers, you can plug an allocator in there, right? So could we maybe use a custom allocator? So it turns out there are a bunch of allocators out there which are faster than the normal malloc, like tcmalloc, which is the Google one. There's rpmalloc. Turns out they're not real-time safe really because they optimize for kind of average case speed, right? So it's very good if you're like having like if you're writing like a web server or something. But they don't really optimize for like the worst case, for like limiting the runtime of the worst case. That's not what they're made for. And in the end, they will always, when they run out of memory, they will always go back to the operating system and request more dynamic memory. So yeah, you can't really use any of those. Yeah, because of all of these reasons. They're not constant time. They typically have locks. They always go to the operating system eventually to actually get memory. What we need, if you want to do this, is a real-time safe allocator, which means it's an allocator that allocates memory in constant time, just single-threaded, and only uses memory that you already allocated up front, right? Because you can't dynamically allocate memory in the real-time thread. You just can't. And the funny thing is, turns out we have not one, but multiple allocators in the standard library out of the box that have these properties. That's pretty great. So we have this thing called std PMR monotonic buffer resource, which is pretty cool. So what you do is you allocate memory up front. I did this like stack memory on array. You can also do like, you can allocate dynamic memory up front. You can, I don't know how you manage this, but like you have upfront allocated memory. And then you plug this into this monotonic buffer object. It takes 3 arguments. So it takes begin and end of the pre-allocated memory. And then what it's going to do is whenever you ask it to allocate memory, it's just going to like advance the head pointer of this pre-allocated memory. It's going to give you a chunk, advance the pointer. It's going to give you another chunk, advance the pointer. It's going to give you another chunk, advance the pointer. The allocation does nothing. And then when it's out of pre-allocated memory, then it's going to call the fallback allocator, which is the 3rd argument. So then it's going to try and go to like the next allocator to get more memory because you're out of memory. And what you can do there is you can give it the std PMR null memory resource, which is something that will always just throw bad alloc if you try to allocate any memory. So this is like your stopgap. This is like your, okay, if you're out of pre-allocated memory, then you're just done, basically. You can't do anything. You're out of memory. You have to handle that somehow. But you can put this together with standard components. And then when we have this, we can create this polymorphic allocator. We can create a PMR vector with that allocator, and everything's great. Yeah, so I talked about the null memory allocator. And we have a very simple working real-time safe allocator going on there, which is just managing a chunk of pre-allocated memory, and then you can use that for a vector, map, set, et cetera, et cetera. So yeah, here we create the vector with that allocator. So that's going to be real-time safe. It's going to be also very cache-friendly because all the memory is like in a block, right? It's kind of cool. There's actually something even better in the standard if you're doing more complex stuff. There's this thing called std PMR unsynchronized pool resource. And that's really, really cool. So what it basically does is you also give it a chunk of pre-allocated memory. And then it basically, it has like pools of, like for each size of the allocation that you want, it has different pools, and each pool has like chunks, and chunks have blocks. And so whenever you ask for, I don't know, 64 bits or something, 64 bytes, you're going to get a chunk. And so there is some overhead in bookkeeping, obviously, over the very simple monotonic buffer resource. And there is also a bit of overhead in time, but it's still very lightweight, and it's still constant, like allocation is still constant time, if this is implemented correctly, which should be. And the advantage of this is that that also can actually deallocate and like reclaim memory, right? So what you do here is you instantiate one of those pools. There are some options you can specify to tune it. And then it takes like this second argument, which is where do I actually take the memory from that I'm managing, where I'm managing this pool. So you give it the monotonic buffer there, right? And then the monotonic buffer as the fallback has the down memory resource. So you know that this is not actually ever going to try to allocate memory because you can't do that. It's going to just take your preallocated memory chunk. It's going to have this like pool buffer on top of that. So that's pretty great. And that's real-time safe, at least until you run out of safe preallocated memory. Is this the most efficient thing, though? I think for some cases it might be, especially if you're allocating different sizes of blocks and stuff like that. If you have like a complex use case, that's good. Like if you're managing a pool of scratch buffers with different sizes, stuff like that, it's great. If you just want a real-time safe std vector, this is overkill. This is like a waste of time and memory. It's like way too complex. It's much, much better to use static vector, which is basically a vector where like it has a fixed size, so not fixed size, fixed capacity, which is not at compile time. It's going to keep all its elements in itself on a stack, right? So that's the best thing you can use. It's much smaller, much faster because you don't have indirection. You don't have to deal with these extra allocator objects, which have a weird lifetime. So that's also kind of complicated. So this is not in a standard library, but it hopefully will be at some point. There is a proposal, P0843, and there's also talk by David Stone about how to implement these things correctly, so that's really cool. Okay, we talked about containers. Let's talk about utilities. What about utilities? So we have std pair, we have std tuple. Obviously, they're on the stack, so they're real-time safe. We have std optional, which is basically just a value in a bool, right? So that's on the stack, so that's also real-time safe. And then we have std variant, and that's really just a union on the stack. So it's actually real-time safe, except variant is a little bit more interesting because it actually depends on how you specify it. So std variant is real-time safe, but boost variant is not. And the reason for that is that there's a slight difference in the specification, and that's like a really good example for like what you have to look for if you try to figure out if something's real-time safe. You look at the spec. This is a really good example. So why is one real-time safe and the other isn't? Well, boost variant has a strong exception guarantee, which it means is what happens if you have an object and that throws on construction, let's say. Yeah, this is like this toy example. You have this object that throws when you try to construct it. Then have a variant, which can hold either an int or one of these things, and you give it an int, and then obviously now it holds an int. But what happens if you try to put one of those other objects in there? So you try to write this throws on construction thing into the variant. It's going to throw, so it's not going to be added, it's not going to be written into the variant. But what state does the variant now have? Right? You have to specify that. Turns out for boost, for the boost version, it has a strong exception guarantee, which means it's going to roll back to the previous value, basically. It's going to like undo the whole thing. If it throws, a little bit like vector pushback has the same guarantee, right? If it fails, it's just going to roll back to the previous state, as if nothing had happened. In order to do that, you need to actually back up the old value before you write the new value, and the way boost does this is by doing an allocation. So that's not real-time safe. The cool thing about std variant is that it doesn't have that guarantee. So if writing something into it throws, it's just going to have this special value, value this by exception. So there's no need to roll back to the old value. So there's no need to allocate memory, so it's real-time safe, right? But like you really have to like look at the spec to see this. Like it's not immediately obvious. All right, what else do we have in the standard library? We have a bunch of utilities using type erasure, like std any, std function. None of them are real-time safe because type erasure requires memory allocation, right? You typically have the stuff on a heap. Std function actually was supposed to be allocator aware. It was specified, I think, in C++11 or something originally that you could put a custom allocator in there, but it never really worked. And so in C++17, we removed it again. There is a proposal somewhere for in-place function, which is kind of like what static vector is to vector. So maybe we will get at some point something like this in a standard library, but currently you have to do it with third-party solutions. Lambda, it's not really a standard library feature, but I just want to mention this here because I need to dispel a myth. I heard people say repeatedly, especially like I heard this here at ADC, people were saying, well, if you create a lambda, like that allocates memory, doesn't it? It's like on the heap. No, it's not. So actually the standard spells out what happens like if you create a lambda. And if you don't do anything else in there that might allocate memory, like if you don't try to catch stuff by value, which is like a std string, which will allocate if you try to copy it, right? If you don't do anything like this, like here, you have like an array which is on a stack, you catch it by value, that is not going to allocate memory. Creating a lambda in itself is not going to be on the heap. So that's real-time safe. If everything that you capture by value is also real-time safe to copy. So that's fine. What is not fine, though, is if you then pass on that lambda to another function, and that other function takes it as a std function, that, again, might then allocate memory. So you shouldn't do that. You should instead template this on the type of the function so it can directly use the lambda type, and then you don't have to do the allocation of the std function. All right. We have another new type of function in C++20. So we had lambdas in C++11. In C++20, we also have coroutines. Coroutines are this new thing. I mean, they're not really new. They're like invented in the 60s. But they're new in C++. So we're a few decades behind, but that's OK. So it's this kind of thing, which you can now do in C++20. This is a very, very simple coroutine that generates the sequence 0, 1, 2, 3. So every time you can yield a value, and then next time you call it, it's just going to like continue the loop, right? So it's like a function that you can leave and then re-enter where you left. This is kind of what a coroutine is. And the way it's specified in C++20, if you then use this coroutine, that is going to allocate memory. So in general, allocating a coroutine frame happens on the heap. So that's not real-time safe. There are lots of cases where the optimizer can optimize that heap allocation away if it sees through like how exactly you use this coroutine and what's going on in there, but you can't rely on that in general, right? So in general, this may perform a dynamic allocation, so you can't create a coroutine on the real-time thread, which is unfortunate. There was quite a lot of discussions on the committee whether that specification is okay. A lot of people, myself including, were not happy with that specification, but we lost. So we have the coroutines that we have. It's fine. You can do stuff like you can rely on the optimizer if it's just like a particular platform, right? So you can actually get quite far with that. There's a talk about this by Eyal Zadaka. But if you want to be portable, you just can't rely on that, right? So what you can do is you can create the coroutine frame up front, suspend it, and then later in the real-time thread, you just resume it. So that, I think, is real-time safe. I haven't really tried this in practice. What you can also do, which is a bit more involved, is you can write your own promise type, which is one of the components you need to put together a coroutine, and then define its own operator new and operator delete, and do something else in there. So that's kind of a bit more work. You can do that. Or my recommendations for now, I guess, is just don't use coroutines in the real-time thread, because it's really quite complicated to reason about. All right. We have a bunch of synchronization primitives in the standard. Since C++11, we have mutexes, we have condition variables, we have all this good stuff. So in C++20, we have even more stuff. We have latches, barriers, semaphores. This is great, right? It's a lot of tools for concurrent programming. Unfortunately, none of this stuff is portably real-time safe, because using any of them will mean that you interact with the thread scheduler or the operating system in some way or another, right? So that is, in general, just not real-time safe. And that's kind of really a hard rule. And so one thing that I actually have seen in the wild a lot in audio code specifically, which I talked about at last year's ADC. I did a whole talk just on that, where people say, OK, I can't acquire a lock and wait on a lock in the audio thread, but I can try to lock. And if I try to lock and I don't get the lock because another thread has it, it's going to just immediately fail and return false, and I can just do something else, like generate silence or something. That's real-time safe, right? Well, yes, that is real-time safe. But once you get to that closing brace, if you hold the mutex and another thread is waiting on the mutex, you have to wake that thread up. You have to interact with the thread scheduler to do that. That is not real-time safe. Or it might be on certain systems and might not be on certain systems. There was like a discussion. I had a blog post about this. There was a discussion online where one Linux expert was saying, oh, on Linux, it's kind of OK. And there was another Linux expert saying, no, it's not. So yeah, I think it's fair to say that in general, if you want to be portable, you can't do this stuff. This is just not real-time safe. You can't use locks in any way or shape or form, not even this. So C++ has exactly one mechanism to synchronize threads that is real-time safe, and that's the atomic, and that's all we got, and that's not going to change anytime soon. Of course, we all use the atomics somewhere deep down in our code. They're very useful. You can use them on its own. If you just have a float, like a parameter, like gain or something, you can just put it into atomic, and then multiple threads can read and write to it, and that's going to be real-time safe. You can use atomics as a building block for lock-free queues and all this beautiful stuff that we use in our code bases. Although I don't recommend necessarily to write this by hand. I tried and failed. Probably not going to go there again. I mean, single consumer, single producer is kind of easy, but once you get into more complicated stuff, it gets really, really hairy. But there are great library implementations, right? So we can also use atomics to make spin locks. And spin locks actually allow you to do this thing that we saw before, the try lock. You can do that real-time safe if you use a spin lock instead of a mutex. And actually, there is a kind of efficient implementation of that where you don't just busy wait and like burn through your battery because one core is just busy, because that's not very efficient. So I have a whole talk about this on last year's ADC. And then also, kind of, you need to make sure that your atomic is actually lock-free, because atomic and lock-free is not the same thing. Atomic just means there's not going to be a data race. So what you need to do is you have still atomic of something. You need to check that it's actually lock-free, which means your platform has intrinsic, your CPU has instructions for lock-free, like atomic reads and writes and compare exchanges for this data type or for data type of this size. And that's obviously true for like bool and int and float and stuff like that on all modern machines. But what if you have a slit complex of double and you want to have an atomic complex double? So that's not really obvious. For example, this MacBook here, the static assert passes. My PC back at home doesn't pass, right? So you gotta check this. And if this assert fails, then what the compiler is going to do, it's going to insert locks into the atomic to make sure that it still behaves, without data races. But there's no instructions to actually make it atomic, so it's going to insert locks. You don't want that. So that's why it's very important to write this static assert if you use atomic with anything else than int, float, bool, that kind of stuff. All right, I'm getting to the end of the talk. There's just one last chapter that I want to talk about, which is standard random number generators. It's something that we use a lot in audio for like humanizing, for example, or for generating noise or this kind of stuff, right? So random number generators are popular. One implementation that I have seen, again, in the wild quite a lot in audio code is this. This is a great, or maybe not so great, but very popular way to generate floats. Typically, you want to generate floats either between -1 and 1 or between 0 and 1. This is kind of the most common cases. So this is a way I see a lot of people use this kind of stuff to generate floats between 0 and 1. So there are quite a few problems with this. The first one is that there's, of course, a bug, because this is a half-open interval, but this code can actually return the number 1. So that's wrong. But there is a bigger problem here. The bigger problem is that people still use std_rand, or like Rant from the C library. And in my opinion, std_rand is completely useless. And it's not because it's a low-quality random number generator and you don't really know like what algorithm it uses. That's not really a problem in audio typically, because we're not doing cryptography, right? We don't have to be like cryptographically secure. We're just generating noise or doing a humanizer or something like that. So we don't need to have like high-quality random numbers most of the time. But there are two other reasons why std_rand is really bad. And if you look into the standard, it says these things. One thing, it says that it's not portable with unpredictable and questionable quality and performance. That's the screenshot from the CPL Standard. Non-portable actually means that it's going to generate a different sequence in every platform. So that makes it difficult to write unit tests, right? So I actually ran into this. And the other thing that's even worse for audio is it is implementation defined whether the rand function may introduce data races. So basically what this means is that the standard library can just call rand like internally somewhere, and it might be a thing that has global state, and the standard library might put locks around this thing to make sure that this global state doesn't introduce a data race. So you might have locks in this function. So never ever, if you see anything like a sentence like this in the standard, you know, whoa, 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 I have to stay away from this. Like, never use this in real-time stuff. Okay, so, we're in modern C++. We have actually 3 other real-time engines in there, so we don't actually have to use std_rand. We have these 3. What does the standard say about them? Well, it says it's amortized constant complexity. I looked at the Mersenne twister, actually quite interesting to figure out how it works. Whenever I don't know how something works, I just go on Twitter, and then a bunch of smarter people are explaining things to me, so that's a great way to learn. So it turns out the Mersenne twister, it gives you a number. It has like an internal state. It gives a number. Most of the time, it's great. But every once in a while, it's allowed to recompute its whole internal state. You don't want to do that on a real-time thread, because that's going to be a lot of computations. We have class template linear congruential engines in there, which is kind of a bit more reasonable. It also says amortized constant complexity, but if I just look at the equation, that seems to me like you can implement that in constant time. So even though the standard doesn't say that it has to be constant time, I'm pretty sure it is, because if it's just implementing that, it is probably fine. This is probably real-time safe. So I have actually also used this in production. It's fine. It is not the most efficient or fastest random number generator you can have. So I'm pretty sure in practice it's constant, but it's not the most efficient one. So I went on a bit of a search, and I found this, ZorShift. This is the random number generator I would actually recommend for real-time audio applications, because basically what it does, it's just like a bit shift and a Zor. That's all it is, right? Those two operations, and that's really, really fast on modern machines. So it's constant time. It's very, very fast. It's my opinion. It's the best one for kind of real-time stuff in audio. It is not in a standard library. I might maybe write a proposal to add it to the standard library, but that's going to take time. So it's not a standard library now, but there are library implementations of this available, third party. Let's pretend we have an implementation of that. And it kind of has the same API as the other random number generators. And let's just say we create one of these, but we still want to generate our floating point numbers between 0 and 1, right? So how do we do that with a standard library? There's this thing called uniform real distribution, and then you have to wrap the random number generator with this distribution. You need to tell the distribution, okay, I'm generating numbers between 0 and 1, and then you call the distribution and give it the random number generator as an argument. And whenever you do that, you get back a float between 0 and 1. So this is how you do this in modern C++. Is this real-time safe? No. Well, so I went into the standard again. Turns out, well, first of all, we have this problem again that the algorithms for the distributions are not specified. So it's really weird. If you just use the naked random number generator, you get the same sequence on every platform, which is great. But if you wrap it into a standard distribution, you don't. You get different sequences on Microsoft, GCC, and Clang, which is very unfortunate. And the bigger problem is that the standard doesn't say what complexity it has. It just doesn't say anything about that. So then you need to figure out, whenever that's the case, you need to figure out, what does it do? How does the algorithm actually work, right? And it turns out, if you dig in and try to figure out what these distributions actually do, it turns out they have amortized constant complexity. So specifically what they can do is they're allowed to, so they're called a random number generator number, and then you do some transformations on it. But they're allowed to like throw out the number and generate a new one. And actually that's unbounded. They can call the random number generator an infinite amount of times. That is, in theory, that's like unbounded. So it's going to happen. It's not really going to happen, I guess, in practice most of the time. But there is actually kind of a reason why this is the case. So again, I went to Twitter and Peter Bindels explained it to me. I'm not going to go through the explanation. There's no time for this. But it makes a lot of sense if you think about it. So basically, if you have a uniform distribution, it can either be constant time or it can be perfectly uniform. But it can't be both of those things at the same time. That's just impossible. And so if you want to be constant time, you can't use standard distributions. So what I'm doing is I'm just doing this same kind of trick as before with the Rant. So I'm using the random number generator, but I'm just doing a division if I have a real distribution, or if you do like an integer distribution, you use something with modulo instead, right? But kind of we all know how these formulae look like. This, of course, still has the bug that it actually can generate the number 1, so that's wrong. So then I just added this hack where if it's like 1, it's going to just subtract a tiny number from it. So this distribution is not perfectly uniform, but it's good enough. It passes all my tests. That's, so it's fine. It works in practice. It's real-time safe. I know exactly how long this is going to take, and that's exactly what you want, right? So this is kind of how you do this kind of stuff if you want to use the standard library. I hope I gave you a bit of a feeling what it's like to use the standard library for this kind of like real-time stuff. And yeah, I think mostly it's okay to live in this world. Maybe we end up just not using the standard library for a lot of stuff, right? We end up using hand-rolled implementations, so third-party stuff, which is okay, you know. If I could have one thing, I would love to have some kind of attribute in the standard which says this is real-time safe, and you can like mark a function with that. And then you would have tool support for that. Like if you would call a function that's not marked with this in your process function, you're going to get some kind of compiler warning or something. That would be great. Actually, we might have different attributes because there's different levels to this. Something might be lock-free, so you want to mark that. Maybe it has a spin lock. Then there's wait-free, which is like the even better, where you know it's never going to like, it's just going to, all the threads are going to continue to make progress no matter what, including a real-time thread. And then there is this like ultimate thing, which is it's going to take exactly the same amount of time every time you call it. So it's kind of tricky to specify these things exactly. So don't think if you're ever going to get something like this in a standard, but you know, one can dream. I think it would be great. So that's all I have. I want to say special thanks to Fabian, Peter, Matthias, David, and Pablo, who helped me a lot with this material. And yeah, that's all I have. Thank you very much.